At which x value or x values does the following function have a point of inflection? Y is equal to x divided by the quantity x squared plus 2. Well, in order to find the point or points of inflection, or the x values where this occurs, we have to find the second derivative. And since there's a variable in the numerator and the denominator, you can either bring this up and use the product rule, or you could use the quotient rule. They're both about the same length, especially when you have a variable that occurs in both the numerator and the denominator. So I'm going to elect to use the quotient rule. So in order to get to the point or the x values for the points of inflection, we have to get to the second derivative. So we have to find the derivative with the quotient rule 2 times. So let's do it the first time. So y prime is going to be equal to the bottom, x squared plus 2, times the derivative of the top, which is 1, minus the top x times the derivative of the bottom, which is 2x, over the bottom squared. All right, so y prime is going to then simplify to x squared plus 2 minus 2x squared, all over x squared plus 2, quantity squared. And again, we can continue to simplify it to be negative x squared plus 2 divided by x squared plus 2, quantity squared. All right, so now we're going to have to find the second derivative. So I'm going to erase these beginning steps, and I'm going to rewrite our simplified derivative over here. So that's negative x squared plus 2 all over x squared plus 2, quantity squared. All right, and now we have to find the second derivative. All right, and we'll apply the quotient rule again for this one. So for y double prime, we're going to have the bottom, which is x squared plus 2, quantity squared, times the derivative of the top, which is negative 2x, minus the top, negative x squared plus 2. And we're going to have to multiply that by the derivative of the bottom, which is going to be 2 times x squared plus 2 to the first times another 2x. And this is all going to be over x squared plus 2 to the fourth, because squared squared is to the fourth power. All right, we can rewrite this as y double prime is equal to negative 2x times x squared plus 2 to the second minus 4x, because 2 times 2x is 4x, and then we're going to have two factors here. We're going to have negative x squared plus 2, and we're going to have x squared plus 2 also, all over x squared plus 2 to the fourth. Well, all of these terms have at least one x squared plus 2. So this 2 becomes a 1. This one over here cancels out and goes away, and this 4 becomes a 3. So we can rewrite y double prime as, and we can also distribute now that the remaining parentheses in the numerator are raised to the first power. So if we distribute this negative 2x through to both terms, we'll have negative 2x cubed minus 2x plus 4x to the third minus 8x, all divided by x squared plus 2 to the third power. And we have like terms that we can combine. Negative 2x to the third and positive 4x to the third is positive 2x to the third. And then we have negative 2x. Oh, actually, that should be a negative 4x, because negative 2x times positive 2 is negative 4. So we have a negative 4x and a negative 8x, so that's negative 12x, all divided by x squared plus 2 to the third power. And now we can set y double prime equal to 0. Let's first talk about critical values for the denominator. Can x squared plus 2 quantity to the third ever be 0? No, it cannot, because even if you substitute negative numbers in, they're going to become positive once you square them. And then you're adding 2 to that positive number and then cubing it, so it's becoming a bigger positive number. So we really only have to worry about when 2x to the third minus 12x is equal to 0. And we can factor out a 2 and an x from both of those terms. And when we do that, we'll have a 2x, and we'll be left with x squared minus 6. And then if we set both of these equal to 0, we'll get that x is equal to 0 out here, and we'll get that x is equal to plus or minus the square root of 6. And now with these critical values, we can create our sign chart for f double prime to make sure that they are points of inflection. So this is for for y double prime, I should say, y double prime. We have negative root 6, 0, and positive root 6. And numbers that we can select in between are negative 1, positive 1, and then greater than square root of 6, 3 is easy, and then less than negative 6 and negative 3 as our test values. All right, so if we substitute negative 3 into our y double prime function, we'll get negative 27 times 2, or negative 54, minus 12 times negative 3, or plus 36. So we're going to have negative 54 plus 36. That's still going to be a negative number. And then in the denominator, it's going to be positive. So we are going to have a concave down section of the function here. When we substitute negative 1 in, we'll have negative 2 plus 12, that's a positive, and we'll get a positive in the denominator. So this is going to be positive or concave up. If I select positive 1 and I put that in for our x values, we'll have 2 minus 12, which is negative 10, that's a negative value, and 1 plus 2, that's 3 cubed is 27, that's a positive value, so we will have concave down here. And now for the last value, if we put 3 in for our x values in our second derivative, we'll get 27 times 2 is 54. 54 minus 36, that's a positive value. And then 3 squared is 9, plus 2 is 11. And when you cube that, that's still going to be a positive value. So it's concave up here. Therefore, we have points of inflection when x equals 0 and x equals plus or minus the square root of 6. So we verified that with our sign chart. And therefore, we know that x equals 0 is a point of inflection, as well as x equals negative square root of 6 and positive square root of 6. So that's 1, 4, and 7. That's actually in answer choice A.